México, existe uma tradição muito arraigada ao capricho do mar. São os homens que, dia após dia, arriscam suas vidas por dinheiro, honra e, mais que tudo, um dos saltadores da quebrada começou nos anos 20, quando pescadores, procurando isca, desafiavam seus companheiros para ver quem saltava do lugar mais alto. Agora, os saltadores pulam de 35 metros, a altura de um edifício de 10 andares. E a profundidade da água é de apenas 4 metros, com a Guadalupe. Nas últimas 8 décadas, só homens saltaram do penhasco. Mas isso mudou recentemente. É a filha do El Cuchillo. Aos 12 anos, ela entrou para o livro Guinness de Recordes por ser a mergulhadora. Hoje, ela é uma lenda viva no México.
Doce sabor do poder. O ex-embaixador britânico Sir Christopher Meyer tem acesso no mundo todo.
O que eu quero falar com você é sobre poder.
A quem o exerce. Redes de poder. Segundas, no Discovery Civilization.
We are about to begin a journey to find out how 1.1 billion gallons of water a day gets to America's thirstiest city, New York. We're going to follow it 150 miles, from rain clouds, down mountains, into enormous reservoirs, through wild waterways, and miles of hidden aqueducts and tunnels. We'll then follow the water right into the pipes that deliver it to its final destination, the faucet in a city home. It's an incredible journey through America's largest municipal water system, all built to quench New York's insatiable thirst.
I'm Christine McKinley. I'm a mechanical engineer.
And I'm John Ranciello. I'm a structural engineer.
Together, we're on a mission to peel back the hidden layers of vital infrastructure under New York.
New York City's water supply starts outside this window. If we're going to follow its flow all the way to a faucet, these rain clouds are where our journey begins. They are made up of condensed water vapor that has evaporated from oceans, rivers, and lakes, and been carried mountains below.
To become rain, the water droplets in these clouds have to become heavy enough to fall to the earth.
Rain droplets form around microscopic dust particles in the atmosphere. When they get large enough, they fall as raindrops. From this point forward, the 150-mile-long trip into the Nitty water system will be driven, and so will I.
There's really only one way to go now, and that's straight down. That's where this guy comes in, because I've never done this before.
So I'm on my way to meet John in an area called the Watershed. This is a 2,000 square mile drainage basin designed to collect the rain that falls on top of the Catskill Mountains. Every water system in the country needs a source of water, and New York City has the model for them all hidden in these pristine mountains. The watershed is so large it is equal in size to the entire state of Delaware. At the foot of these mountains is a reservoir. Along with the rainwater, that's where we're headed.
The rainwater falls and is absorbed by the soil right here. It then seeps into the earth until it reaches the water table. Think of a reservoir as a drain in a sink. And these mountains, the sides of the basin, bringing the water down to the drain.
Hey, Christine! Eventually, the water finds its way into streams that speed its trip downhill. To follow the flow, we are going to chase one of these streams.
Now this is just a small stream, but hundreds of these combine for a constant flow of water into the reservoirs below. If you stretched out all the tributaries in the system, you could connect Miami to Seattle.
Pacific, the Reservoir, and the Gilboa Dam.
This is the northernmost reservoir in the system. It's 150 miles from the city. It's also the fastest filling reservoir, with a capacity to hold 17.6 billion gallons of water.
The greatest challenge in the design of any reservoir is keeping all the water in place.
This 120-foot high dam helps control the water in the reservoir, preventing this whole area from flooding. Oh man, as a structural engineer, I love it when we can get this close to a dam.
The dam is a huge wall built into the bottom of a valley. The sheer weight of its structure counteracts the pressure being applied by the mass of water. And because that water pressure is greatest at the base, dams are built incrementally thicker towards the bottom. But if this enormous piece of infrastructure were to fail, the results would be catastrophic. Local residents would barely have minutes to escape before 40 feet of water would cover their homes. The residents of Baldwin Hills, California, outside of Los Angeles, know this all too well. On December 14th, 1963, a pencil-thin crack in the Baldwin Hills Dam quickly grew into a 75-foot crater in a matter of minutes. 292 million gallons gushed from their reservoir, creating a 50-foot-high wall of water that consumed everything in its path. In the 77 minutes it took to empty the reservoir, 65 hillside houses were ripped apart, 210 homes were damaged, and most tragic of all, 5 people lost their lives in a flood that spread panic across the Los Angeles area.
At New York City's reservoirs, dam maintenance is one of the many responsibilities of New York City's Department of Environmental Protection, or DEP. This one agency is in charge of the entire system, from the reservoirs upstate all the way until the water is delivered to faucets in the city. But after 80 years of wear and tear of the Gilboa Dam, they have In 2005, a study found that the bedrock beneath the dam was at risk of sliding out of place, collapsing the whole structure. The DEP took immediate action, installing 80 steel anchors through the face of the dam for structural reinforcement. They also took temporary measures to lower the water levels and alleviate pressure on the dam. They are now in the early stages of a project in America.
But even with the overhaul of the dam underway, 150 million gallons a day is still being sent from this reservoir towards New York City. To guarantee its safe delivery, the DEP have a dedicated police force with a unit specially trained to combat acts of terrorism and sabotage. This elite unit can access every part of the infrastructure, including these dam walls. Today, they've allowed me to join them on their training exercise.
Basically, we deal with two major functions: infrastructure protection and emergency response. If there's an emergency, we have to be in place to get our people where they need to be to do the job.
If this unit was unable to reach every part of the infrastructure, the entire system could be at risk. Training sessions like these allow them to safeguard the water delivery system for 8.2 million New Yorkers. $260-foot dam. We just dropped down from it. These guys are ready to do it 24/7.
But they're not out here alone. Hidden somewhere in this 2,000 square mile watershed is a top secret monitoring facility. It's the nerve center of practically the entire reservoir system. I've been given special permission to see how it works.
Very few people get to see the inside of this place. If the wrong people found out where it was, they could create absolute chaos, not only throughout New York, but across 3 neighboring states.
This is the DEP control room, where 85% of New York City's reservoirs are monitored and controlled.
How's it looking today?
Looking good.
Operators in the control room watch water levels, power failures, water quality, and any security breaches with sensors and hidden cameras throughout the system.
Can you see what goes on in every part of the...
We're keeping an eye on it, yeah. We're keeping an eye on it more ways than one.
This team works around the clock to keep New York City's water flowing.
We'll monitor storms all across the country. That are coming in. That's going to affect our area, our watershed.
When the weather is calm, it moves like clockwork. But with a storm brewing over New York State, the control room must act quickly. The last thing they need is the system flooding on their watch.
Even before the storm actually progresses towards our area. We're going to be a continuous monitoring of those elements and to see what type of precipitation we can expect.
Knowing what's coming will allow the team to take measures in advance to control water flow control. To rebalance the water in the system, they have put in a call to increase the amount of water being released towards New York City. John is there to see it on its way to the next reservoir.
Now about to enter the Schoharie intake facility. Intake facilities help manage the flow of water between reservoirs. Keeping it on course takes a specially engineered system that begins under this building. An 18.1-mile tunnel carries the water out of this reservoir to a natural creek that takes it the rest of the way. And it's Mike's job to control that flow.
What we have here is measuring what is going actually into the tunnel.
So this is the water that will eventually get to New York City residents?
Yes, and at some point you'll get to get a nice cold drink of it.
But it has a long way to go before it arrives at the city's faucets. Next it will flow down a raging river, and so will we. Let's go. We're on a journey to follow the flow of New York. We've reached final distance.
Gallons of water are held in 19 interconnected reservoirs that supply the thirsty city. This is so much water that if it were emptied onto Manhattan, the entire island would be flooded to a level of 110 feet. The Schoharie Reservoir is one of the collection reservoirs that refills the system.
Up to 618 million gallons of pure cold water a day can be sent to the next reservoir right from this building. But it can't just be opened like a faucet. This takes precision on how much needs to be sent to the tunnel. The more water that's needed, the more the gates need to be opened. But these gates don't open easily. It takes a 5-ton gantry crane attached to a giant piston to lift them. So the first thing we have to do is get the piston in place. And I have the honor of moving it.
Tell me when. I don't want to overshoot it. That's probably pretty good. Next thing we'll have to do is drop that thing down and get it on top of the gate.
Most of the equipment has been here since the reservoir was built in the 1920s. And it is still responsible for sending water south towards New York City.
Right on down to the bottom. A little more. That's good.
These nuts are going to secure this in place. We don't want it to move at all because this gate is heavy. Altogether, the gate and stem weigh 20 tons.
All right, now I just need to get the crane into position.
How much are we going to open up this gate?
Right now we're shipping about 150 gallons a day through the tunnel. We're going to open it up to 163 million. We just got to stick the pin in here and we should be ready to go.
The piston and crane are attached to the gate, and it's time for some heavy lifting.
Just lift this thing up far enough so that the spacer here will slide right underneath that pin. Anytime you're ready, just hit the button.
All right, here I go.
And that should do it.
Nice.
That's 5 million easy wet.
New York's water is always flowing between the reservoirs, down tunnels and waterways like these. But to keep it moving requires an enormous... When in the Catskill Mountains, engineers had to figure out how to move the water through this challenging landscape. The only way to do it was to use the steep terrain to their advantage and harness an abundant power supply, the force of gravity. By building tunnels through the steep mountains and commandeering existing waterways like this creek, water is moved from one reservoir to another.
This water is the exact water released from the Schoharie Reservoir upstream.
Now we're headed straight downhill. By the time this water reaches the next reservoir, its elevation will have dropped 300 feet.
Controlling the energy in the water is the key to the entire system. As it enters the 123 billion gallon Ashokan Reservoir, the energy of the mighty Esopus Creek is cut off by the Olive Bridge Dam. Built across the natural riverbed in the deepest part of the valley, the dam literally stops the river's flow. Look at this beautiful valley. You can see the water on one side, and you can see that they built the dam in the deepest part of the gorge here.
Yeah, all these surroundings, that's exactly what the engineers were looking for to make this whole system work.
Yeah, almost. There was one thing that was already here that really didn't work for the engineers at all. Down here, there was 8 towns with 2,000 people. They all had to be displaced. It was part of the cost of building one of the greatest infrastructure systems in American history. Today, New York City's residents rely on 3 separate watershed systems: the Delaware, the Catskill, and the Croton. Each one has its own aqueduct that carries the water from the upstate reservoirs toward the city. Seeing how the water enters these aqueducts is the next stop on our journey. I'm at the much water in the Delaware system to be allowed into the aqueduct unregulated. To manage the amount of water going into the aqueduct, there are 6 sets of valves 160 feet beneath the surface of the reservoir. These valves are from 1947 and they're still working. The valves open and close like a faucet to moderate the water exchange between the reservoir and the aqueduct. That's incredible. You can hear it. You can hear the 700 million gallons a day that come through here to New York City. Even though the water is moving only a few miles per hour, it carries the energy and momentum of a freight train. This is the beginning of the aqueduct, where the water flows right down into the city. The system's 3 aqueducts run for a total of 278 miles and have to transport thousands of tons of water in each mile of their length. It's too dangerous to follow the flow of a working one, but we do have an alternative. The original aqueduct in the city system. We're in Sleepy Hollow, 30 miles north of the city. The New York State Parks Confined Space Team has invited us to join them on their annual inspection of the old Croton Aqueduct. Although this 41-mile tunnel isn't currently in use, it's still connected to the New York water system and needs to be checked for structural integrity.
And space like this is incredibly, even when it's dry. You never know when there's going to be a dead air space where there's not enough oxygen, where there are noxious fumes being released from decomposing matter.
Come on, keep walking still.
The tunnel was built on a constant 13-inch per mile incline, again utilizing gravity as a source of energy. Implementing such precise engineering in 1837 was a monumental challenge.
This tunnel was built way before any sort of technology that we have today. Just mules and manpower.
It's amazing to think about.
Yeah, if you could see these bricks, they were laid in 1837, just in pristine condition.
To maintain the consistent 13-inch per mile incline, the tunnel had to be built into the existing topography. Where we are right now, the aqueduct was cut into the line to contain the water. A modern aqueduct with 3 times the capacity now does the work of this old one. But we're still connected to a working reservoir, so this tunnel can be brought back online if necessary.
There's still a huge plug at the end holding all the water back. If that thing went out, we'd be in trouble. One of the objectives of coming down here is to check to see for any signs of trespassing. Guys, any chance that we're going to see anybody or anything down here?
People have gotten in here before.
And not just people. This is the perfect environment for bats, but not for humans, as we're about to find out.
Here we go. Low 2. Okay, guys. Ready to get our mask on? Put on your mask, off your helmet.
Helmet off?
When you run into an oxygen shortage in a confined space, you must evacuate immediately. It's time to get out of here.
We've been following New York City's water supply. Now we're 30 miles north of our final destination, the faucets of New York City, but we've hit a problem.
Pop your helmet.
While inspecting the old Croton Aqueduct, we've hit a pocket of dead air. We're following safety protocol for confined spaces, and we are getting out.
Bring up from here. We're in good air now.
Yeah?
You should be able to pick up fast.
The three working aqueducts move the water towards the city's northern border. From here, it is destined for a system of smaller reservoirs that feed into tunnels that go deep under the city. The tunnels empty into shafts, distributing water to mains, finally delivering it to businesses and residents. That under cities, there is no mechanical filtration. Instead, the water is minimally treated with chlorine to kill bacteria and fluoride for dental hygiene. But in the Croton watershed, where development has increased near the reservoirs, there is concern about the rising level of contaminants leaching into the water. The federal government has ordered the DEP to begin filtering the Croton water, and fast. We're on the northern edge of the city in the Bronx, where the DEP is updating the Croton system for the 21st century.
The DEP is building a huge underground water filtration plant on this 9-acre site right here in the Bronx. To dig this crater, 100,000 dump trucks full of dirt had to be cleared out. The plant is being built with 500 million pounds of rebar. Look at this.
This construction site is insane. It's like a small city.
Yeah, we gotta split up to cover it all. I'm gonna go down here.
All right.
See ya.
When construction is complete, the raw water will be brought in by a tunnel from the new Croton Aqueduct. Once in the plant, the water will first be fed into a chamber and mixed with a chemical that makes it flocculate, meaning the particles of silt will compress into larger pieces, making it easier to filter them out. From there, it will be sent into a sand filter to remove the silt. Then a UV chamber will kill any bacteria that remain in the water, as a safer and more effective alternative to the chlorine that is used today. I want to get a first-hand view of how the water will come into this plant, and there's no one better than Brian to show me. He's one of my old classmates from engineering school and one of the contractors on this project.
Brian. Hey, John, how's it going? How you doing? Very good. You guys getting a lot of work done down here? Yeah, we're working on the UV piping. It's part of our treatment system here. There's enough piping on this project to go around the Indy racetrack about 5 times. We're really getting inside this tour.
And I can tell we're getting closer to where the water will enter the plant.
Connected 10 months ago, and eventually the water will come into the pump station here and get pumped up into the treatment plant. It's probably the last time we get a tour of this area, because when it's finished, flood zone.
Few people ever have a chance to see a pipe big enough to carry 270 million gallons a day. And this is only for 10% of the city's water.
This is where the water is going to come into the plant. Hey John, this pipe here, 144 inches in diameter. That's 12 feet high. 144 inches. Look how big this is. I can't reach the other side. My car could go through here. The water is going to be rushing through here, waiting to be cleaned. This is where it all begins.
This filtration plant is a massive challenge, but there's even a bigger one ahead. 80 feet are the clean. See where the water will go.
Welcome.
Hi there. Bernard Daly is the lead engineer of this project for the DEP.
How far does it go? About 4,000 feet. So we get off here and walk down, right? How are you doing?
Yeah, all right. I think we're close to the tunnel boring machine. The mole. That's what's digging this tunnel. It's getting warmer. Louder. And closer to the biggest, loudest machine I've ever seen. We've followed the New York City water supply to where it enters the city at its northern borough, the Bronx. Now I'm beneath the streets in a tunnel that will carry water out of the system's first ever filtration plant and on to 8.2 million thirsty people. So we're about 100 feet down, and above us would be gas lines, electric lines, and streets, people. Tunnels like these are the main distribution lines for New York City's water, and there is one machine that is vital to their construction. This is the tunnel boring machine with the mole. The real action happens in front. So there are several cutting heads that grind through the rock and send it back overhead. There's a belt up here that carries back the rock and muck. And then moves 5 feet forward and braces itself again. This is still the mole. It goes forever. We're going to try and find the control room. This mole is 380 feet from its head to its tailing gear. With 29 individual cutting heads attached to the front of the mole, it's the best way to create this 7,800-foot-long tunnel. These machines are responsible for creating most of the tunnels in New York, for roads, subways, and water. This machine can't be driven like a car, it's more like a spaceship.
I'm going to bring you into the brains of the TBM now. Chris and Ike are the operating engineers that are operating the TBM.
Chris and Ike have the most important jobs in this tunnel. They have to keep the mole moving forward through the rock while making sure everyone down here is safe. The weight of the city is on their heads.
Alright, well, if you watch what I'm doing now, you'll get to see how it's starting up. I'm going to start the motors now. They're going to turn the head up.
As we move it, it's moving slowly.
Oh, we'll start to move?
We'll start to move.
It's very slow.
It's very slow.
Oh, I feel it. Yeah, I feel it.
You can see it.
It feels like we're sort of bouncing back and forth, like we're headed in and then...
Yeah.
The screen up here, there's an actual live shot of the rock and the muck coming back from the cutting head. Over the top of us.
While we're mining, the material will come out from one belt, land on the other belt. I have to know if either one of those belts stopped. You know. I just dragged the back end of the machine up to catch up to the mole.
So the piece that the 5 feet that you already cut, you're now supporting.
The head advances, they drill 4 holes, support that ground.
Okay.
Do it again, all the way on.
Got it.
See the bolts as you walk through. Stay easy.
This tunnel will eventually be lined with concrete and filled with a series of 9-foot diameter pipes to carry the water from the plant. But while they're drilling, they need to temporarily support the walls to keep them from falling in. So these we were just talking about, they were putting them in for...
And these are called Swellex rock bolts.
But these rock bolts can only support the stronger rock. If the rock has fractures in it or is soft, they have to install round case steel sets to reinforce the structure of the freshly drilled tunnel. If they don't, it could collapse on everyone in here. I want to get closer to that cutting head. Is there any way we can get closer?
turns, I can get you in.
Okay.
You'll see the head there.
That's the head? Oh my God.
But these bolts, I want to get in. This particular tunnel will take the water to a nearby reservoir. Then on to more tunnels that will carry it through the city. Coming off these are a series of shafts that connect to the large distribution mains. The larger mains feed smaller mains under each street before connecting to service mains, delivering water to individual buildings. Our final destination is in sight, but in a system with 6,000 miles of pipes, we still have a long way to go.
We follow the flow of New York City's water from the reservoir into the city. It has been delivered through tunnels to mains on each city block, the last link before it is delivered to buildings. Mains are the most vulnerable link. Traffic, even electricity from the subways causes 700 water main breaks every year. Each one of them starts as a trickle, hidden deep beneath the pavement.
There's been a leak reported, and we think it's located in a water main on this block.
Because water seeks the path of least resistance, the leak we are looking for could have come from anywhere and been carried far from its source. The repair teams need to find the leak, and the last thing they want to do is dig up the pavement in the wrong place. In situations like these, the DEP calls in specialists to find the leaks that no one else can. They're known as the Leak Detection Unit.
So what do we have here today?
Hey, how you doing? We got a leak spilling right here, right behind us. So we're checking out water main to see if there's a leak on it, which is causing a leak condition in the building.
Using state-of-the-art technology, Gil can actually hear the water as it leaks from the pipes.
Right, this is what we call an outstation. And what this unit does is amplify sound so that we can hear it. Let's give this a sound, see what we get. Oh yeah, we got good sound here.
Yeah? All right. Sounds like
water rushing.
Water rushing. Maybe some whales. Sounds like whales going by.
Well, it takes a trained ear, but after a while you get used to the sounds and you know what you're looking for.
Gil now has to check the sound at another access point further along the block.
Further west. Good sound. Very good sound, yes.
Then the distance between the two access points.
That's the total footage between this bulb and that hydrant gate bulb. All right, so now we're going to put the footage into the computer and we'll scan it and see what it gives us.
Okay, let's see if we got a problem or not.
The two outstations relay data to a wireless correlator to find the leak.
Okay, see that spike right there?
Yeah, I do. It's huge.
So it's telling me from red, can you see what it's saying there, footage?
149.7 feet.
From this unit here. And we'll see where that puts us.
You're confident that at 149 feet, there's going to be a leak?
There's something there, yeah.
Armed with his high-tech equipment and years of experience, Gil can locate even the faintest drip deep under the pavement.
Now we're going to put this right on the top of the street, and we're going to be able to hear what's beneath the street.
Yes, if the leak is strong enough where it's making enough sound, we can pick it up with this device. Watch.
So, doctor, what can you hear?
I hear some sound.
The leak is marked out for the water main repair team, so they can start digging.
It's non-stop. One shift after another. Once they find a leak, these guys attack the problem until it's fixed.
Today, I am their eager apprentice, and I can really appreciate what these guys do.
You're out here working in the elements all the time. I mean,
yeah, we work in all the elements, snow, rain, sleet, 95 is better. We out there. Not too many people say they can do manual labor anymore.
You don't get much more manual than digging a hole.
No, you don't. You can knock into a gas line, electrical line. That's why with the jackhammer, we don't go no more than what you see here. Yeah, the level of the cement, maybe 1.5 feet down with the jackhammer, then everything else is by shovel or by hand.
So you've come across that before where you've actually
Yes,
hit?
I've never hit a gas line, but I've hit an electrical line and actually melted my blade. Maybe a short mushroom, 1.5 feet, poof. That's about it.
And no chance we're going to hit a power line today?
This hole here is nothing. Nothing.
So this is an easy hole?
This is an easy hole, yeah.
And here I was thinking I was working hard. But it's all paying off.
Oh, I got a line here. Oh, it's leaking. See that?
Oh, man.
See that push?
It's coming right out. I can literally see the hole in the water pipe. It's shooting out. This is an obvious problem, and we got to get it fixed quick. This leak is coming off a private service line. And that means the building owner will get their own. And that'll be it. We're in your hands.
Okay, well,
problem solved.
Everybody drinks on me.
Water all around.
To move all the water across the massive city requires a lot of energy. This energy is provided by water pressure. Here's how it works. Reservoirs on the northern edge of the city are kept to the same level as the top floor of a 6-story building in Manhattan. Because water seeks its own level, it will rise back up to 6 stories high. This way, the water can move up through many city buildings without a single pump. But for hundreds of skyscrapers, 6 stories of pressure isn't enough.
So before we end our journey at a faucet, I'm going to see how the pressure is raised on top of the city. We're almost at the final destination for New York City's water supply, one of the millions of faucets in the Big Apple. We follow the water all the way from its source in the mountains of New York to the main. Once it enters the buildings, there is enough energy provided by the pressure in the system to lift it 6 stories high. But in a city known for high-rises, many buildings need to give the water a boost.
I'm on top of a 10-story building, so the water is going to need some help to get up this high.
Without the use of a rooftop tank, the water could be pumped directly to each fixture, but that pump would have to be running constantly, and it would use to pump water. That fills up, and then gravity and pressure can send the water downward through the building's pipes and into the fixtures.
The company's been doing this for 142 years. These water tanks are as much a part of the skyline as the skyscrapers.
Rosenwalk is one of only 2 wooden tank companies left in the city, and today I'm working with one of their crews to install a new one.
This is just nothing to strap in?
So when you're working up here, you just have to really watch your step.
The old tank is out, we put the base down, and we're going to surround ourselves with these cedar staves.
You want to put one on? You could put Atar. Watch it.
Yeah, I can put one of these in?
Yeah, watch him, Atar. Just watch him, though. Watch your top. No, you got to watch your top. Watch your dowel. The most important thing is that you have to keep it straight.
And that's straight?
Kind of hard.
Kind of straight.
Virtually weatherproof. They require minimal maintenance and have the same insulation value as 24 inches of concrete.
I've quickly been surrounded by cedar staves. We're about to get closed in.
Now we have to wrap the staves with metal hoops to hold them in place.
They're loose right now, but we're going to tighten them, go on the inside, and then hit the boards so that everything is nice and snug, creating a perfect seal for the water. All right, let's go inside the tank. See that? This is how these staves have to be. Take a whack of the stave right there. Whack, heavy whack. Heavy whack. Push that bad boy. Listen, look, baseball swing. See that? Let's switch here. Here we go, left. Left to hit, right, good.
It's a slugfest in the tank to get the staves tight against the hoops on the outside.
Yeah. Take it from here, right? A little tighter.
You good?
Yeah?
I'm starting to feel increasingly claustrophobic.
Silly me. I thought I'd be more comfortable outside.
All right, I'm the only one up here not swinging a hammer. I ain't letting go of this roof. We are 130 feet above the sidewalk.
Yeah, but I think that
It's a great view, but I can't wait to get down.
The pipes inside the tank are in place. This for another 35 years. Once the water is turned on, it flows through the building until it reaches the end of its and our epic 150-mile journey.
Pure New York City water, straight from the tap.
And we've followed it from the clouds into the watershed and seen how it is collected and managed in the reservoirs.
We experienced how gravity carries the water from one reservoir to another.
And how aqueducts were built to bring it towards the city.
We were part of how the system is being modernized for the future.
Look how big this is. I can't reach the other side. My car could go through here.
And saw how the improvements are being tied into infrastructure that is over 100 years old.
Constant maintenance and continued innovation are necessary to keep the walling to 8 million people.
Here we are.
Thank you.
Cheers.
And it will continue to be this way as long as anyone calls this city home.